Hi everyone and welcome to the internet. What we're going to be doing in today's physics lesson is having a look at generators. So hopefully by the end of this lesson you're going to be able to describe how generators work. And we're going to look at two types. We're going to look at an alternator and a dynamo. To start us off though, we've got two questions on the screen there. So have a go answering these two questions based on our previous lesson in your books for me. So I'm going to give you about 3 minutes to have a go at that. So, first question, there are three ways that we can obviously increase the potential difference. Give yourself a mark for each of these that you've got right. So the first one, move the wire faster. Secondly, use a stronger magnetic field. Or finally, use more coils. You could describe that as use more loops or use more wire. Any of those descriptions are fine. Then for number two, when we're actually describing what happens when we drop our magnet through a tube versus just a metal ball and explaining the effect, then we've got up to 4 marks for this. Your first mark is for saying that as the magnet falls, it induces a potential difference in the metal tube. Second mark, if you've said that the potential difference makes a current flow in the metal tube. Third mark is for saying that the current generates a magnetic field of its own. And the final one is for pointing out that magnetic field is in the opposite direction to the one actually exuded by the magnet itself, and therefore the magnet is repelled, making it fall slower. And then obviously we can just make a final statement just pointing out that the metal ball doesn't do any of those things, so it just falls through the tube. So add it up, scores out of 7, and write those scores in your book for me. Okay, so what we looked at in our previous lesson was this idea of an induced potential difference. So what I want you to do is just explain how we can induce a potential difference in a coil of wire. Hopefully we remember that the main point here is that to induce a potential difference, we need that wire to cut some field lines from a magnetic field. Now, the way that we can do that, you've got a couple of options here. First one is that we can move a magnet in and out of the coil, or we could move the wire within a magnetic field. So either of those two ideas, we are still going to be cutting those magnetic field lines, therefore we will still induce a potential difference. If you didn't get that answer written in your books, obviously make sure you've got the point on the screen written down so you know how we induce that potential difference in our coil of wire. The first device we're going to look at then is the alternator. Now, in an alternator, we've got a coil of wire that's spinning between the poles of a magnet. Now, because we've got a coil of wire that's spinning between the poles of a magnet, obviously the wire is cutting the field lines. So as a result of that, we are going to generate a potential difference. The key thing here is it's going to be an alternating potential difference, because that potential difference we're generating is going to change direction. So get those 2 points written down, and what I've got for you in the next bit is actually a little animation to help you see this, because it's quite hard to visualize what on earth I'm saying in those 2 sentences there without seeing it. So got a little animation to show you that in a moment, but get those 2 sentences in your book first of all. So what we've got in this little animation then is the setup for an alternator. So what we can see is we've got our magnets, so we've got our north poles in the blue and the red are the south poles, and then between them you can see we've actually got a coil of wire attached into our circuit. Now what we're going to see is what happens when that coil of wire spins, and down here in the bottom right corner you can see what happens in terms of the voltage. So if we just hit play, then we can see as it's spinning, then we get positive into the negative, back to the positive again. Now, if you watch it as I play it this time, watch the side of the coil that's facing up at the point that we're in the positive. So this point, this one, and then it's in the negative, positive, negative, positive. So what we can see there is that as that coil is turning within our magnetic field, then we are going to get an alternating potential difference, because what we're actually seeing is it's changing direction. If we look at the diagram that I've given you on the screen at the moment, then we can see we've got our magnet, we've got the coil of wire passing through the centre of the two poles, and the coil of wire is then attached onto those two metal rings. Now, those are called slip ring commutators. Do not confuse them with the split ring commutator we talked about previously. This is a slip ring commutator. Very similar, very annoying that it's very similar, but you've just got to learn it. Now, you will also notice just to the side of those slip ring commutators are these little carbon brushes. Now, they're not physically attached in terms of being secured onto the slip ring commutators, but they do brush against them. So they're in contact, but they're not physically adhered to them. Now that's really important because, as we've said, what we're going to see is that coil is going to turn within the magnetic field. Now, if that was all attached, then we'd end up tangling the whole thing. Because it's just resting against the carbon brushes with the slip rings, then it doesn't tangle. So what we see is as the coil is turning, then those slip ring commutators are always in contact with the carbon brushes, but they're just kind of brushing past, as the name carbon brush suggests quite nicely. So make sure you've got the 3 points written down, especially the bit that highlights it's a slip ring commutator. And if you really want a diagram, then you can obviously pause the video and draw that for me. You don't have to though, and obviously the PowerPoint is on my website and also in our Google Drive, so that you can just download it later, print a copy if you've got access to a printer, or draw your own version if you want to at a later stage. So I'll just leave this up for one more minute to let you write down those 3 points. As we saw in the little animation, the graph that we get goes from the positive to the negative. And what I've given you on this slide is just a little sort of diagram, if you like, showing you what's happening to the position of the coil and put it just beneath the graph so we can tie those two things together. So we know that what we're going to do is generate this potential difference that is going to switch between the positive and the negative as the coil rotates. So if we start with our vertical coil, then right away at the far left hand side of the graph, then it's neither positive nor negative, it's neutral. Then what we find is as that coil starts to rotate, then it goes into the positive, and when it's at that 90 degrees to its start position, that's its maximum positive potential difference. Obviously the coil then keeps rotating, and that means the potential difference is going to start to decrease. And when it's in that vertical position again, we're back to 0. As it goes beyond that vertical position, then we're in the negative potential difference, reaching the maximum negative potential difference when it's at the horizontal position. And then as it continues to rotate back to its start position, we see the change in the potential difference until it's back to zero again. So we get this constant cycle of the positive, then the negative, back to positive, then the negative, as the coil just rotates. So make sure you've got that sentence written down, and if you want to do a little sketch of the graph, you are always welcome to do so. I'll leave this up for about another 40 seconds to give you a chance to make any notes you wish. One of the key places that we actually find these alternators is in a power station. So what we actually have is this massive coil of wire all the way set up through our power station. So we've got numerous versions of this setup. And what we actually find is that the generator is a rotating electromagnet inside those coils of wire. And they're going to be spinning at a frequency of 50 Hertz. Which is why when we actually look at mains electricity, then it has a frequency of 50 Hertz, because we're getting that alternating current being generated by these alternators within our power stations, and they're doing that at a frequency of 50 Hertz. Our second device we're going to look at is a dynamo. Now the key difference between our alternator and our dynamo is that alternators are going to produce an alternating current, or AC, whereas a dynamo is going to produce a direct current, or DC. So what we're seeing here is we've got two different devices that are able to generate two types of current. So alternating current in the alternator, direct current in the dynamo. Now, what we'll find is it's called a direct current because it's not changing direction. It's always staying in the positive. And what we're going to see is a similar setup. We've got our coil in a magnetic field again. But because we're always staying in the positive, hopefully this tells us we're not going to be using slip rings. We're going to be using split ring commutators. Because if we think back to what we said about motors, the way it can always push down on the same side of that coil is by having it so that it's not a complete circle of metal it's attached to. So we've got those two half circles which rest against the carbon brushes, which means you've always got the positive being the generated current. So in this case we're making a direct current, so we're using split ring commutators. You can see the gap in the actual middle there. And then as it turns, it's always going to remain in the positive region of the graph, as we can see on the right hand side. So dynamos makes a direct current, and it's always going to be in the positive direction because the current doesn't change direction. Make sure you've got those points written down, and if you want to do the little sketch of the graph, of course, feel free to do so. So what we've said here with our dynamo is that the direction of our potential difference isn't going to change because the coil is connected to that split ring commutator. So that means it's always going to be in the positive direction, for example. The one thing that we can change though is the magnitude of the potential difference. So what we're going to find is it's not just a horizontal line, because if it was a horizontal line that would tell us that neither the direction nor the magnitude is changing. Instead, we've got that curve, as we can see at the bottom, kind of like a series of little hills. Now that tells us the magnitude of our potential difference is changing, because obviously when it's closer to our x-axis, then that's a much smaller potential difference than when it reaches the top of that peak, when it's the largest potential difference. So key thing here is that the direction does not change, but the magnitude does change. So make sure you've got those 2 points written down. What we need to know now is how we can again increase the output. Now, because we're looking at similar devices here, they're both generators at the end of the day, then the way we can increase the output is the same. So whether you're asked about increasing the output of an alternator or increasing the output of a dynamo, doesn't matter, we can write the same things. So there's 3 that you should learn here. First one is use a stronger magnetic field, and we can obviously explain that in terms of stronger magnetic fields have more field lines, therefore more will be cut each second. Second one is using more turns in the coil, and again we should be able to explain that. And finally, spinning the coil faster. So each of those we should be able to explain based around the work we've done on electromagnetic induction in our previous lesson. So make sure you've got those points written in your books for me. I'll leave this up for about another minute to give you a chance. Final thing for today's lesson then is to have a go at answering our plenary questions. So 3 of them are on the screen for you, and everyone can have a go at the same questions today. So I'll leave these up for about 4 minutes to give you a chance to really have a go answering them in your books. As always, you can find the answers to the plenary over on my website, scienceright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.